Hey there, my name is Brittany Gagne and I am the packaging lead at 88 Brewing here in Calgary, Alberta. Today's video, we're going to be reviewing a course that I took through a scholarship through the Pink Boots Society. This was through the Chartered Institute of Brewers and Distillers, and it was the General Certificate in Packaging Beer. So I got this scholarship through Pink Boots, like I mentioned, and I wanted to make this video to go over all of the things I learned, what I felt was the most important, the most valuable type of information in the course, so that you guys can watch this and hopefully gain something from it as well. So we're gonna go and talk about things like beer history, packaging, different forms of packaging, different types of materials. We're gonna go over packaging trends, labels and boxes, all different types. We're gonna touch on transferring, pasteurization, and a lot of other things. So I'm gonna be covering quite a bit in this video. Feel free to take notes if this is something that you're interested in. But let's go ahead and get started here. Beer was originally stored in wooden barrels, then glass blowing was invented in 1903. This is where we get glass bottles, and from here on out, this was the most popular form of smaller packages in beer up until about 1935. This is when the very first can run of beer happened, and it was called Kruger's Finest Cream Ale. So now about 60% of the US market is sold in cans, $20 billion industry, and that is quite impressive. It is interesting to me that globally, most beer is still packaged in bottles, even though it is better for the beer to be completely sealed so you don't get any kind of like light pollution. To be in a can, it's better for the beer. So interesting that a lot of international markets prefer glass bottles. So let's talk about large form pack. So in 1785, the beer engine was invented for casks. In 1936, the artificial carbonation in beer is introduced in steel containers. 1970, pressurized kegs replace casks in most markets. Now let's cover different types of packaging. So for primary, we have things that contact the product directly. These are items like bottles, cans, caps, and labels. Secondary packaging materials include things like flats, cardboard packs, boxes, and pack text. Tertiary packaging is used for transportation, so these are items like pallets and plastic wrap. Packaging trends. So plastic bottles may become more popular as technology advances. Right now, it's only about 3% of the US market, but 33% in some Eastern European countries. Plastic bottles can be pasteurized, so no need for aseptic filling. Aseptic filling is beer that is free of spoilage microbes, but not all microbes. Pasteurization is essentially applying heat to remove spoilage organisms, and this was invented by Louis Pasteur in 1864. Aluminum is 5 times more expensive than steel, so steel becoming more popular in certain areas because of this. Both can be infinitely recycled, but aluminum is easier to recycle and cheaper to transport. It's quite a bit lighter. Packaging materials. So we have glass bottles. There's typically 3 different colors: clear, amber or brown, and green. I thought it was pretty interesting, the material breakdown of glass bottles. It is the vast majority silica, which accounts for about 70%. Soda ash is worth 15%. Limestone is 9%. Refining agents, we have 6%, and then there's colorants and deodorizers added to the materials to make different colored glass. Clear glass is made from selenium, manganese, and cobalt oxide. This decolorizes the glass and makes it clear. Amber and brown glass is made from sulfur, carbon, and iron salts. Green glass is made from chromium oxides. And I also thought this note was super interesting. So glass bottles have bumps on the base, and these are actually a code to trace the mold that these bottles came from in case there are any defects. So something cool to look out for next time you are drinking a bottle of beer. Now moving on to cans. So original cans were stainless steel, and they weighed about 8 times more than aluminum ones launched in 1935. About 75% of aluminum ever produced in the world is still in use today. Really quite impressive. There's nearly 1 billion tons out there as we speak. 20% of the market is actually steel cans, and only 8% is aluminum. And they are made from a mix of steel and aluminum. The internal coating of water-based epoxy lacquer applied to the inside prevents metallic taste because beer is acidic, and you don't want that breaking down any of those like metallic flavors. So moving on to labels and outer packaging. So let's talk about offset printing. So offset printing requires no labels. You print right on the can, and it doesn't affect the recyclability of the can. Really large minimum orders for this kind of printing prevent smaller breweries from going this way. A note about what printing registration is. This is something I learned in the course. Basically means that all colors appear as one to the naked eye. If it's off registration, that's when you can see the separate colors on the can itself. Another type of outer packaging is sleeving. So these are shrink sleeves that go around a can or a bottle, and then they are heated and they shrink to fit tightly onto the package. They're typically higher quality graphics, and they are hard to recycle. So this is one of the downsides, because the shrink wrap actually burns when it's being recycled. Also, minimum orders again. Some types are being phased out due to health concerns from PVC. And it's also worth noting that these shrink wraps can hide defects in the cans or bottles, which you don't want. Another form of printing that is gaining popularity is digital printing. This is really high print quality. And of course, it's very easy to change a design just to change like an actual file if it's a digital print. It is slower than other methods and more expensive, so probably why it hasn't really taken off yet. The next type of printing is screen printed labels. These are printed directly onto the bottle, again, very similar to offset printing. It's a mix of inks, inorganic, and UV cured, so they can't be recycled into flint glass if they are printed this way. The next and most popular form of labels for bottles or cans is wet glue labels. These are made from paper of cellulose fiber from wood. Paper labels must have 30% tensile strength of a dry label. Tensile strength is paper's resistance to rip when stretched. Labels also have to be resistant to detergent so the product can go through a bottle washer. And this method, the wet glue label, is the cheapest method, but it does need to be stored in temperature and humidity controlled environments. The next type of label is a self-adhesive label. These are laminated and made of various layers. The release coat allows the labels to peel away easily. The face stock, which is the main design or the exterior print, and then the top coat protects. They are a higher print quality than wet glue. They're hard wearing and waterproof. They're about 2 to 5 times the price of wet labels, so obviously quite a bit more expensive. They're slower to apply, and the liner or the webbing that is left over from when the label comes off of it is not recyclable. So now we're gonna move on to large pack containers. We'll start with kegs. So more than 85% of kegs are stainless steel at this point in time. They're made from type 304 stainless steel and have a lifespan of over 30 years. So definitely a great investment, whether you're a medium or a large size brewery. 50-liter kegs are the cheapest form of the package. They're 50% cheaper than cans and about 30% cheaper than bottles. I wanted to cover the anatomy of a keg and just throw a photo up here and show what part is what. So we have the chime, which is the rim on the top and bottom of the keg. Next is the neck. This is the threaded section where you can go ahead and put in the keg filler or the tap. Then we have the valve, which is inside the neck. The spear, this is the internal down tube for filling and dispensing. And the sump, which is a shallow well at the bottom of the keg. These are rated to 20.7 to 75 bar. And if you're not familiar with bar, 1 bar is equivalent to 14.5 PSI or pounds per square inch of pressure. Sizes in kegs vary from 10 to 163 liters. 20 and 30 liters are most popular in Europe, and US uses barrels, which makes things a lot more confusing. But I'll cover what each one means. So a 6th barrel is a 20-liter keg. A quarter barrel is a 30-liter keg, also known as a slim quarter or a pony keg. And then a half barrel is 58.7 liters. So I suppose this would be just about equivalent to a 50-liter keg here in Canada. There's a few different types of kegs. We have the din, which is tall and narrow. The euro, which is short and wide. And then we have plastic coated kegs and plastic one-way kegs, which are PET kegs. They're made of polyethylene terephthalate. Also similar to kegs are casks. This is about only 1% of the US market, but 8% of the UK market, super popular in the UK. Green beer goes into these casks and finishes fermenting. This is called cask conditioning. Originally, they were made of wood. They're mostly metal now, and up until 2015 were made from aluminum and stainless steel, but they are now only made from stainless steel because aluminum contamination has been tied to Alzheimer's, so definitely not what we want going forward. The smallest cask out on the market is typically around 25 kilograms full, and they go up to 100 kilograms. The most common size is a firkin, and that is 40.9 liters. Pin is the smaller size at 20.5 liters. Cask beer is recommended to be stored at 12 degrees Celsius, or it will essentially go bad and be ruined. Now let's cover secondary packaging. So paperboard multi-packs. There's 4 different types. We have fully enclosed, basket carriers, wraps, and clips. These are widely available. They are lightweight, they are easy to cut, easy to form, recyclable, and inexpensive. They do need to be controlled storage-wise between 18 and 22 degrees Celsius and at a relative humidity of 60 to 70%. Another option is corrugated boxes and trays. These are the most recycled packaging material. They have good stacking strength if they're dry, they're readily available, they're the least expensive of all, but they perform quite poorly if they get wet. Crates, these are mainly used for glass bottles that can be returned. They do tend to warp or deform over time, and this is called creep. They have a 10-year lifespan. They're made from up to 40% recycled plastics, and they do weaken over time, and it's hard to get to the right color with recycled plastics, so something to note if you want to purchase those in a large quantity. Shrink wrap is another exterior packaging option. It's light, requires less storage space, inexpensive, recyclable, but many places don't accept it to be recycled, and some retailers won't actually stock anything that's shrink wrapped because of this. There's also plastic ring carriers. This is the latest option, lowest transportation cost. They are recyclable, and some are photodegradable, which means they break down in the sunlight, though it does take a while. Now into tertiary packaging. So we'll start with pallets. These are typically made of wood or plastic. Plastic is stronger and lasts a lot longer, but wood is more environmentally friendly. We also have locator boards. These are used for stacking kegs. They need a special forklift, but it makes stacking kegs very, very stable and more safe than traditionally stacking them on top of each other. Plastic film is a very popular way to wrap up a pallet. The first method is spiral stretch wrapping. This is the most common and the cheapest. Heat shrink hooding. This is when a plastic bag is pulled over the pallet and then shrunk to fit. And then stretch hooding, which is similar. A plastic bag is stretched over the pallet instead of being placed and then shrunk. Now let's move into packaging line operation. So there are 4 steps to prep containers for filling. The first one is depalletization. This is when containers come off a pallet. The second is conveying. This is when you basically move those packaging materials from one area to another. Cleaning, this is extremely important. This is clean in place before being filled. And the 4th step, which is inspection and sorting. The final step of brewing is transferring or filtering the beer into the final product tank or a bright tank to get it ready to be packaged. Some beer, especially in smaller breweries, is not filtered and it's packaged directly from the fermentation vessel or the conditioning vessel. Just some notes on specifications for beer, ABV or alcohol by volume. This is an alcohol percentage. It is calculated by the original gravity, the sugar concentration of wort before fermentation. pH or potential of hydrogen. This essentially is measuring how acidic or basic a solution is, and it can indicate detergent contamination. Something I noted during my studies was haze. So high haze in beer that's meant to be clear can result from collapsed foam and need refiltering. There's also something called chill haze, which shows up in cold beer, but as the beer warms up, disappears. So you get a hazy beer turning into a clear beer as it goes up in temperature, which is kind of interesting. The color of beer. So incorrect color could indicate alcohol dilution, low in color, or detergent contamination. This would be high color. It is best practice to always sensory the beer before packaging to catch any contamination or off flavors. The brewery that I work at, we sensory the beer every morning before packaging. Usually we get 3 or 4 people to try it to make sure nobody misses anything. DO, also known as dissolved oxygen. This is ideally under 100 ppb or parts per billion. CO2 and nitrogen, N2. This must be in spec or it can lead to filling problems. Another very important thing to note before packaging is the final product tank or the bright tank pressure itself. So a loss of pressure or low pressure can result in quite a bit of underfills, foaming, and high DO. High pressure can create out of spec beer, high losses, and underfills. So again, something you don't want. You kind of want to be right at that sweet spot. Another thing to note, or another term to note here, is FPT, residence time. So this is your final product tank residence time, how long that beer has been in that tank, and the minimum time a beer needs in a tank for pressure to equalize. Now moving on to beer transfer principles. So you want to achieve a low shear, gentle, non-turbulent laminar flow. Low shear means minimal disruptive forces and gentle circulation. Laminar means even flow. Turbulent means lots of mixing. You want to minimize fobbing or foaming during transfer. Minimize or eliminate oxygen ingress, tighten all clamps, connection points. Regular equipment checks will help this. You want to prevent beer dilution and brand mixing as well. And you want to prevent metal ingress from pipes and fittings, avoid contaminations, minimize temperature increases and time in the vessel. You would like to maintain spec pressure to avoid any kind of breakout. The ideal temperature for packaging is around 0 degrees Celsius. Another thing to note here is that CO2, carbon dioxide, only remains in solution in beer at pressures that are above atmospheric pressure. So moving into filling and the filling processes. The first item here is gravity filling. So your final product tank needs to be above the height of the bottle filler, and the flow is controlled by a float valve. The next type is isobaric, short tube fillers. Isobaric means single pressure. That means the container and the product supply are at the same pressure. In this method, beer filling continues until it reaches the base of the vent tube. This means the liquid can't flow up the vent tube due to the pressure being equal in both. It's fast and it fills top to bottom. Isobaric long tube fillers, on the other hand, fill a little bit slower and they fill bottom to top. Non-isobaric long tube fillers, these are typical for smaller systems. There's no pressure evacuation or pressurizing step. This means the container is at atmospheric pressure and the supply is below 1 bar or 14 psi. The next is electro-pneumatic fillers. These are typically short tubes. They're most common in high-speed operations, and they are controlled by a computer system. Something that happens in a lot of different canning lines is foaming. This is basically displacing oxygen in a container. For bottles, something called a water jetter can be used. This sprays water into the bottle. A bottle knocker can also be used. This is a spring-loaded hammer. And a ultrasonic foamer can also be used, or an ultrasonic transducer, to release some of the oxygen in that container. With cans, we at my work use something called a DO buster. This is a dissolved oxygen buster. Basically forces CO2 down on top of the container to push any oxygen out. And then it is ideal to seal that can as quick as possible after it's gotten its lid on it. Now let's cover pasteurization and sterile filtration. Pasteurization is heat applied to reduce microbes. Heat sterilization, on the other hand, is much more intense heat to kill all microbes. PU is a pasteurization unit. One pasteurization unit is achieved by exposing beer to 60 degrees Celsius for 1 minute. Each beer has a specific pasteurization unit number. For lagers, it's typically between 5 and 20. For stouts, it's below 20. And for non-alcoholic beer, it's between 40 and 120. Over-pasteurization can lead to burnt flavors and cause beer to taste metallic or papery. This is beer staling. This can also change the beer's color. Pasteurization is typically controlled by computers, especially in larger breweries. Another method for pasteurization is the tunnel pasteurization method. So this is for small pack filled containers. It takes about an hour to move through, so not very time efficient, and the exit temperature is between 20 and 25 degrees Celsius. The next method is flash pasteurization. This is when the product is pasteurized before filling. It's typically a higher temperature than the tunnel pasteurization, about 72 degrees Celsius. It's held in the holding tube for less than 1 minute and then cooled to 4 degrees Celsius before filling. The entire process only takes a few minutes. High pressure is required for this to keep the CO2 in solution as the temperatures rise. It's smaller than the tunnel pasteurizer. It can be used for all packaging types, not just cans and bottles, and is a shorter processing time and less expensive. There is a risk of recontamination of microorganisms, especially no and non-alcoholic products. Beer has to be cold for filling, so package warmer may be required to help avoid condensation affecting the labels. And on to sterile filtration. So this removes yeast and microorganisms through very fine filters, 0.45 microns big. Sterile filtration does not equal sterile beer. Some microbes will pass through, but nothing harmful or anything that will spoil the beer. Sterile filters aren't meant to clarify beer, so it should be clear first. Otherwise, the filter will just clog up. No heat is used in the process, so no flavor deterioration. There is a risk of contamination because this happens before packaging. Now, just to clarify something, so aseptic versus sterile. Aseptic means the beer is free of beer spoilage microbes, and sterile means it is free of all microbes. Now moving on to quality. So quality management, quality control, these are checks at the end of a process. Quality assurance, these are checks throughout a process. TQM, also known as total quality management, this is the Japanese method. QMS, we have quality management systems. These are for large companies, interdepartment policies and procedures. ISO, the International Organization for Standardization, ISO 9001. You can get certified through audits. HACCP, pronounced HACCP. This is the Hazard Analysis and Critical Control Points. This controls the physical, chemical, biological hazards and allergens. Now for principles, we conduct hazard analysis, identify CCP, establish limits, monitor corrective action, verify, and record keeping. For this to be effective, other controls must be in place. PRPs remove most hazards at the source. A PRP example, so the first one is food safety policy. The second one is cleaning and housekeeping. This is very, very important in a brewery. Number 3 is pest control, super common as well, especially if you're in an area that has a lot of pests. And number 4, product recall and traceability. This is, if you have a can or a bottle that has a date code on it and a batch number, you can trace if there's any kind of contamination that gets caught out in the field by customers. GMP is good manufacturing practice. The main components are written programs and implementation. Water safety is very important, and basic environmental and operational conditions to manufacture safe food. GLP is known as the good laboratory practice. This is equipment effectiveness, calibration, validation, training, safety, sampling design, and traceability. This assures quality and integrity of non-clinical lab studies to support research, marketing, permits for regulated products. Dissolved oxygen and beer flavors. So let's talk a little bit about this. So oxygen in beer causes Number 1, an increase in chill haze, which I mentioned earlier. Chill haze is caused by malt-derived proteins and polyphenols from malt and hops bonding together and forming a colloid, which is suspended matter in the beer. It appears when beer is cold and goes away when it's warm. Oxygen in beer can also increase the permanent haze formation. It can reduce your bitterness and create some undesirable flavor compounds. These can come across like cardboard, leather, stale, kind of papery type flavors, and it reduces your shelf life. Oxygen pickup can come from various different sources, like valves, unions, which are 2 pipes joined together, pumps, processed gases, pipes, vessels, and fittings. Less valves and unions equal less oxygen pickup. The maximum oxygen level in beer should be 0.1 milligrams per liter or lower. Controlling oxygen, we'll just go through a few different methods on how you can do this. So control points, we've got filtration, dilution, which is diluted beer with deaerated water, packaging, the DO measured in line before the filler and also right after the filling and closing process to see if you're getting any oxygen in those containers. Pasteurization, the heat can increase oxidation, so you want to be careful with this. For measuring DO or dissolved oxygen, you can use a optochemical method. This is the most modern method. There's a layer of plastic with luminescent dye. The LED is the illuminated layer, and you can use a photodetector to measure the light. Electrochemical monitors reduction of oxygen by using electrical voltage. The number of electrons consumed at the cathode equals the concentration of oxygen in the sample. This method is slower than optochemical because the oxygen electrode can be coated with beer or cleaning solution. You can also use a TPO meter. Modern TPO meters are lab instruments that automatically measure HSO, which is headspace oxygen, DO, which is liquid dissolved oxygen, TPO, or total packaged oxygen, and CO2, carbon dioxide. Some of the causes for high headspace oxygen include ineffective jetting, bubble breaking, and undercover gassing. These are methods to remove oxygen. Insufficient container pre-evacuation to remove oxygen. So before that container goes in to actually get filled, it's not removing the oxygen effectively enough. And then also insufficient can flushing can cause this. High DO can come from pre-filling steps or during actual filling. Now let's talk about antioxidants. Antioxidants stop oxygen reactions by already being oxidized. Some breweries add antioxidants right before packaging. These include sulfites and ascorbic acid. Most commonly used are sulfur dioxide and potassium metabisulfite. Sulfites are naturally produced in beer during fermentation, so adding more must be monitored to avoid dangerous levels. Sulfite can cause severe allergic reactions, so it has to be listed on the label. Now moving on to hygiene. The risk of contamination is highest during packaging. Water can be a source of biological and non-biological contaminants. Iron equals a metallic taste. Discolored can ends, this could be bromine used in pasteurizer water, and it may contain pesticides and nitrates. Gases, a tiny amount of grease in gas supply can affect a large volume of beer. Absolute rated filters can be used to prevent contamination. You should be checking gases that come into direct contact with your beer by bubbling the gas through water and tasting the water. Lubricants can also contaminate beer, so always use food grade lubricants. Now on to biological contamination. Pest control, don't leave the doors open or leave dirty kegs around. Build in low risk areas. Don't build in areas that are known for having pests. Microbiological, fungi and bacteria. Only non-pathogenic bacteria can survive in alcohol. The most common is lactobacillus and pediococcus, which produce off flavors and reduce pH. Some produce CO2, which can cause bottles to explode. Fungi like yeast. Culture yeast is yeast for fermentation, and all other types are wild. For microbiological control, the hygienic design of equipment, smooth, easy to clean, chemical and heat resistant, is one way of doing this. Another way is effective cleaning and sanitization. The third way you can control this is raw material and product sterilization. And the fourth are conditions to inhibit microbiome growth. So low temperature, low pH, alcohol, CO2, and hop aids can help. Of course, you should also monitor the quality with regular testing, regular maintenance, and repairs of all equipment that you have in the brewery. In order to detect microbiological contamination, a sampling tap, which is attached to the tank, sterilized with a flame or sanitizer before taking a sample, and sealing. These can be tested at various points during packaging, before packaging. Another way to sample is the septum membrane sampling. This is a rubber septum in housing, which is pierced by a needle. Or you can also use a continuous sampler, which takes samples continuously during packaging. Samples are cultured and tested in a lab to see if they're contaminated. So to summarize, this course had a lot of great information in it, but it's definitely more catered to very large scale operations. I hope you gained some helpful tips and information from this video and got to take a little bit of a behind the scenes look into beer packaging. Thank you for watching, and leave me a comment down below if you have any further questions.